In 1800, William Herschel placed a thermometer beside a rainbow. The strange part was not that sunlight felt warm. It was where the greatest warmth appeared, in a patch that looked completely dark. Herschel wanted to know whether every color carried the same heating power. He passed sunlight through a prism and moved thermometers across the spectrum. The temperature rose from violet toward red. Then he moved beyond red, outside the visible band. The thermometer rose higher still. His paper reports the strongest heating roughly half an inch beyond the color, with an effect detectable farther out. Herschel had not found darkness. He had found radiation his eyes could not register, infrared. Less than a year later, Johann Wilhelm Ritter looked beyond the other end of the rainbow. His detector was not a thermometer, but silver chloride, a chemical that darkens in light. Its reaction accelerated beyond violet, where the eye again saw nothing. That became ultraviolet. Two invisible territories had been found by two different effects. Heat on one side, chemistry on the other. The lesson was larger than either discovery. Nature did not have to be visible to become measurable.
But measurement still depended on what the instrument was made from. In 1848, William Thomson, later Lord Kelvin, proposed an absolute scale meant to be independent of any particular thermometric substance. The modern Kelvin scale developed through later work, but the direction was clear. Temperature should belong to universal physics, not to one tube of mercury. Soon after, Gustav Kirchhoff defined another universal ideal, a body that absorbs all incoming radiation and emits a spectrum determined only by wavelength and temperature. A small hole in a heated cavity could approximate it.
The ideal was elegant. Measuring it was not. In the 1870s, Samuel Langley developed the bolometer, an extremely thin metal strip whose electrical resistance changed when radiation warmed it by a tiny amount. Mirrors and prisms could feed one narrow band of radiation at a time onto that strip. A change too small for skin and often invisible to the eye became an electrical deflection. Scan across the wavelengths, record each response, and the spectrum could be drawn. Herschel's thermometer had discovered an invisible region. The bolometer began turning that region into data.
The data revealed a pattern. Hotter bodies radiate enormously more energy, and the peak of their spectrum moves toward shorter wavelengths. That is why a heated object begins in the infrared, glows red, and then moves toward white. Wilhelm Wien found an equation that matched the short wavelength measurements remarkably well. For a time, it looked like the answer. But the improved data did not agree at long wavelengths. A classical alternative worked there, yet when extended in the other direction, it predicted energy climbing without limit. That failure later became known as the ultraviolet catastrophe. The curve was forcing a choice: preserve the old assumptions or take the measurements seriously. In 1900, Max Planck tried to construct one law that survived across the full spectrum. His paper begins with the experimental problem. The latest measurements had shown that Wien's formula was not universally valid. Planck treated the walls of the cavity as resonators, exchanging energy with the radiation field. Then, in the counting that made his law work, he divided their energy into elements proportional to frequency. Energy equals Planck's constant times frequency. This was not yet the complete modern idea of a photon. Planck himself did not begin by announcing that nature was built from light particles, but the formula fit. At long wavelengths, it approached the classical result. At short wavelengths, it approached Wien's. Between them, it followed the measured curve. A reluctant mathematical move had opened the door to quantum physics.
A clean curve can hide the hard part. No detector simply displays nature. Radiation is absorbed by air, scattered, reflected, mixed with nearby sources, and reshaped by the instrument itself. A bolometer has its own response. So does a telescope. Scientists calibrate those responses, estimate contamination, compare competing models, and carry uncertainty through the calculation. That creates a fair question. If a model helps clean the data, are we only finding what the model expected? Sometimes that danger is real. The answer is not to avoid models. It is to constrain them with laboratory calibration, independent measurements, known physical mechanisms, and tests that could have failed. That discipline became cosmic in the 1960s. At Bell Laboratories, Arno Penzias and Robert Wilson found excess microwave noise wherever they aimed a large horn antenna. It was unpolarized, nearly the same in every direction, stable across the seasons, and about 3.5 degrees above absolute zero. Their short 1965 paper reported the stubborn measurement. A companion paper supplied the interpretation. This could be relic radiation from a universe that had once been hot and dense. Detecting the background was powerful. But another question remained. Did its spectrum really have the black-body shape expected from a thermal beginning?
NASA built COBE to find out. Launched in 1989, the Cosmic Background Explorer carried FIRAS, the Far Infrared Absolute Spectrophotometer. Its crucial idea was comparison. FIRAS could place the sky on one side of the measurement and a carefully controlled black-body calibrator on the other. Engineers adjusted the reference until the two signals nearly matched. Most of the common signal canceled, leaving the tiny difference. Measuring that residual could be more precise than trying to measure the full brightness of either source alone. The universe and a human-built cavity were placed in effect on the same balance. In the original mission film, COBE scientist Michael Hauser described why evidence this rare deserved such care.
Cosmology, as you can understand, is a very difficult problem to study objectively. We are given very few fossils on the beach, if you will.
The match was extraordinary. Across the FIRAS range, the cosmic microwave background followed a black-body spectrum at about 2.725 Kelvin. At ordinary plotting scale, the measured points in Planck's curve sit almost on top of each other. But that famous graph is not raw detector output. The signal also contains emission from our galaxy, instrument effects, and the dipole created by our motion through the background. Those contributions must be measured and accounted for. The result is trustworthy, not because processing disappeared, and not because one beautiful line proved a cosmology. It is trustworthy because the calibration was physical, the corrections were testable, the residuals were small, and other observations fit the same history. This story began with a thermometer placed where a rainbow seemed to end. It passed through chemically darkened paper, an absolute scale, a black cavity, a platinum strip, a broken equation, and Planck's energy elements. Nearly 2 centuries later, a satellite compared the microwave sky with a laboratory reference and found the same thermal law written across the universe. Theory helped decide what to measure. Instruments exposed where theory failed. Calibration separated a fade signal from everything traveling with it. Then independent evidence asked whether the reconstruction still made sense. The cosmic microwave background is often called a baby picture of the universe. Its spectrum is something quieter and perhaps more remarkable, a cosmic thermometer. The universe cooled, the radiation remained, and humanity learned how to read it.